since A is compact, this means that A here is contained in finitely many of these. Let's call them, so you have finitely many like this of the B's, and I just, I'm not sure whether it's the first, but there are finitely many of these that cover it. And so in particular, by one of these is like, right, one of the indices here is the largest one of those, right? And so this means that it's actually contained in the largest of these. Let's say that the largest of these is Bn, right? So you have this for some n, right? But this here, remember that this here was the complement of Cn, like this, right? So this means that A have nothing in Cn, right? So this means, but A was a Cn was, so Cn intersected with A is empty, but Cn was contained in A. So this means that since Cn was assumed to be contained in A, right? These were subset of A. Then this means that Cn, so this here is, this means that this here then implies that this thing here is Cn, right? So you have that one of them was empty, but that we assume that none of the sets Cn was empty, right? Okay, was that clear? Sorry, yep. Okay, so that's right. So I'm trying to prove this theorem here, right? And it's not super complicated, but it's a little bit involved. And so I'm trying to, of course, this is always a great idea, and it's kind of like an important thing in this class. And also, if you take other math, more advanced math classes, is that when you're trying to prove something, there's things that are really easy to prove, but then there's things that are much more complicated, right? So one thing is that you try to prove it. Another thing is that you try to explain to others the proof, right? And so in either case, if you can divide it into substeps, right? And so this here is a substep in the proof. And so in a minute, we will see why this here is relevant. And so this is sort of answer your question, right? I mean, how does this come up, right? And in a minute, you see how it comes up. So let me get back to that question in just a minute.
Are you able to explain the last remark again?
Yeah.
That you're saying?
So here, so again, the BIs are open and using compactness, because all of the BIs cover A, then finitely many must cover it. But the BIs are nested in this way, that they are increasing as subsets. So if I'm thinking about maybe this here is the one where the index is large, this then contain all the other. So it's actually equal to, in that case, it would be equal, this really is equal to like this. So again, so this means that A is contained in the complement of Cn. So in other words, there is no element in A that are in Cn, right? That's what it means. So there is no element in A that is a Cn. This is that this thing here is empty. But the Cn's, remember that the Cn's was assumed to be subsets of An, right? So this means that there is nothing in Cn that is not in A. So this is really just equal to Cn.
So is that essentially just creating a contradiction?
And that's right, and that's a contradiction, because now this shows that this one here, this Cn, is empty. but they were all assumed to be non-empty. Right? Yeah. Okay. Okay. So this is like, yeah. Sorry.
I have a question about to get the contradiction. You said like if it is the case that the intersection of the CIs is in fact empty, then A is contained in them. Why?
Right. Okay. So if the intersection of the CI, right. So here, sorry. If they I want to prove this. So I'm assuming that this is the case, and I define the BIs to be the complement of the CIs. So if there is nothing in the intersection of all of the CIs, then it means that the union of the complements must cover the whole set. Right? Because, right, so if you take anything even in X, if you take anything in X, it's not in all of the CIs. So this means that there is some I so that it's in the complement of that CI, right? But that's exactly this. Okay, so you're asking why is it relevant, right? And that's a good question. And I will answer it in a minute, but I will kind of elaborate. I will give you an example where I have it, and then we will eventually see how to get to that example, okay? So the next thing is that suppose I have the same setup, but now my sets are, the closed sets. So I have this setup again. So this is like a corollary of the lemma that we just proved. So we have X comma D. This is metric space. And we have A here. It's a subset of X is compact. And now my sets CIs is going to be, so CIs here, these are going to be balls of radius Ri and center Xi. And there will be balls like this. And I'm assuming that they are nested. So in the same way, I'm assuming that this thing here, the centers change, the radii and the center change, depending on I. They're all these closed ball where it's like less or equal to the Ri. So I'm assuming that the next one is contained in the previous one. Okay? And then I'm making one more assumption, is that the Ri goes to 0. Okay? So I have that. So just let's observe that these sets here, they are nested by assumption. They're closed, right? Because it's this closed ball. So they're closed subsets. Also observe that each of these balls contain the center. So, right? So this means that each of these balls is non-empty, right? So it's automatic that they're non-empty, right? Okay, so now I claim that the intersection of all of these balls is just one point. So now the claim here that the intersection of these balls here, these closed balls here, is a single point. Okay. Yeah.
Sorry, how do we know that each of balls contain the center?
Because you know, if you take a ball, so if you take a ball here in any metric space, this is the y in the space in this set, so that the distance from x to, now I take the open one, but similarly with the closed, this thing here is less than, sorry, this here is y. Sorry?
It contains its own center, but not like one single point across all the balls.
Yeah, so that's right. So I'm just saying that, so if you plug in y, x for y, right, you get 0, right? So this is definitely, so this here, x definitely is in here, right? And I'm just saying that each of these guys is non-empty, right? Okay, so now, and then I want to claim that actually there's something in the intersection of all of these balls, and I want to claim that there's only one thing, such thing. There's a unique thing that is in the intersection of all these balls. Right? Okay, so now first I want to prove that this thing here is non-empty, right? And sorry, and this here should have been the closed balls like this. But you see, this just follows from the lemma, because each b, you know, because each bri xi is closed and non-empty, each is closed, non-empty, and the family or the sequence of balls is nested, right, by assumption, right? By assumption, we assume that this thing here is our I plus 1, xi plus 1, that this thing here is contained in the previous, right? So by assumption, so we use the lemma, and this is the CIs, right? And the CIs are closed, and they are indeed nested as they should be. And they are all non-empty just because they each contain their own centers, right? You know, yeah.
So by making that assumption that they're nested, are
Yeah.
we like implicitly making an assumption about like the structure of xi?
We're making some assumption, that's right. We're making some assumption about, right, so, we're, you know, and right, we're making some assumption about that when you make this assumption about nested, there's some assumption about the centers, the distance between centers, and there's also something about the radii, that, you know, how large is one radio relative to the other, right? Because if you imagine that this here is BRI like this is this, so, and the picture would be kind of contain the boundary, and then the next one, but the next one may be out here on the side, but it's supposed to be contained in it, right? So you see that the center may have moved. This here was the xi, and the next center may have moved. It may have shifted quite a bit, right? But of course, you know, this here is the Ri radius, and this here is the Ri plus 1 radius, right? So you see that there's some sort of relation, right? But okay, so we have that it just follows from the lemma that the intersection of all these closed balls is non-empty, right? Yeah.
Doesn't it just follow from like the assumption we made
Yeah, that's right. So it follows now from that Ri, that's why we're using that Ri goes to 0. Because suppose that you have two elements, right? Suppose that you have X here and Y. Suppose that they are in the intersection of these guys here. Right? Now, look at the distance between X and Y. Well, they are intersections, so this means that for each I, so for each I, we have that X here and Y is in this guy here, right? So if it's in this ball here for a I, then you can use the triangle inequality. Right? And this thing here is bounded by, this here should have been a Ri. This here is bounded by less or equal to, because I have this bar, Ri plus Ri, so 2 Ri. But this here holds for all I. This here goes to 0. So this means that this here implies, as you say, this here implies that the distance had to be 0. But this is part of what it means to be a metric space, that if the distance is 0, then the 2 points are the same. Okay, so that was actually, so the whole correlate was really quite easy from the lemma. Okay. And so now the question is, so this is your question, is why is this relevant in this Bolzano bias stress, right? I mean, they're maybe not so interesting. I mean, the lemma and the correlate on its own, but there are tools to prove this Bolzano bias stress theorem. Okay, so let me try to first explain the idea, and then we go to the proof. So we have this metric space, and we have a subset. And the subset here is compact. Subset is assumed to be compact. Then we have a sequence, xn, and this sequence here, so this is a sequence contained in A, and we want to prove that they exist. So want to find a convergent subsequence. Remember that here, I mean, just that there's no assumption, I'm not talking about some Cauchy complete set space or something like that, right? So in this case, I really have to construct the convergent sequence, but I also have to kind of construct the limits, right? And so this is where, like in particular, like the limit, this is why we want this thing here to have a unique intersection. Okay, so that's what I want to do, right? So you have this space, you have the subset that's compact, and you are given a sequence. So now I start with and before I actually get to the proof, let me just try to explain the idea. So this is sort of before the proof. So I want to make an observation. So if I am in this iteration, and suppose now that I take, so I have A here, and I take some R, think of R as being really small, and then do what we just did a little while ago. We're looking at A here is covered by A. You can write A as a union of these balls here, where the center is anything in A, right? So again, that cover A, and so this means that finitely many cover A, since A is compact. So I can write A here as contained in, and then R. Now I have to be careful because this is not the X. Probably I should use a Y here. Sorry, just to not confuse it with the sequence that I have. Okay. And so it's contained in the union of balls like this. Ym, right? It's contained in the union of finitely many balls like this. Okay, so far we haven't used our sequence, right? But now, of course, I can say that we were given a sequence, right? We now have finitely many balls, right? So, and there are like infinite many elements in the sequence. So it means that there is one of these balls, finite many balls. So for one of them, for one, maybe more than one, maybe all of them, but for at least for one of these balls, there are infinite many elements in the sequence. Let me be very precise what I mean by that. So by that, I mean, of course, the sequence could be like a constant sequence. What I mean that for infinitely many n's, xn is in one of these balls, right? So let me just write that out, just to be totally clear. So meaning for one of these balls, there are infinite many n's such that xn is in that ball. And let's say that this is Y3, whatever, fine. So that's infinite many n, okay? So now I can just think about that one ball, right? And I can just think about the sequence. Instead of the original sequence, I think about a subsequence that is contained in it, right? Because so meaning, this means that there is a, therefore, there is a subsequence of the given sequence that is contained in this ball. Okay. Now, okay, now I want to somehow repeat this process. I want to repeat this process. And again, I haven't quite started the proof here, but I'm just trying to explain the idea, right? So this is like this is like a step in the proof that you then, for the right radii, etc., has to use over and over again, right? And so now so I want to repeat this process, and for that I need to remind you that if you take a metric space, if you have a metric space, so record that if X here is a metric space, A here is a subset, is a compact subset, A is a compact subset, and B here is a closed set, is a closed subset of X, well then A intersected with B, right? The intersection of, if it's compact, it's also closed, right? We proved that. And so this is the intersection of two closed sets. So this is closed. This is contained in A. And now we proved last time that if you take so this here is a closed subset. This is closed. And it's contained in A. Since A is compact, if you take a closed subset of A, then this here is also compact. So this is also compact. Okay. So now let's continue that string of thoughts from over there. So how do we now repeat this? So I have a set. I have here, maybe I should throw it even bigger. I have here, this here is my space X. Then I have some subset. This here is A. A is compact. I cover it with balls here of radius, and I now have that finitely many. These are balls of radius R around some Y's, right? Finitely many. There's finitely many of these balls, and they cover A, right? Then these sets here are, of course, not closed. And so I'm looking at this ball here, these finitely many, and I just take the closed balls. Now I want to cover, right? And I found that for one of them, there was a subsequence that was contained, in fact, in the open ball. So even, therefore also in the closed ball, right? There was a subsequence of the original sequence. That's the ball I'm focusing on, right? Now this ball I can then cover by balls of radius. So I'm covering this. So cover this by balls of radius R over 4. So I'm going to write this thing here in the same way. I'm going to write this. This here I now know. This thing here, I'm only interested in things that are contained in A. So I know that if I intersect it with A, then this here is compact, right? I know that this is compact. That was because this here was closed, right? And A was compact, right? So this here is compact. So this means that if I can write that set here, I can write that set as, so I can write this set here So I have, so so I start with A, that's compact. Then I find a ball so that a subsequence is contained in that ball, right? This was that ball. Then I'm looking at, so this is like the process I start with here. This is step 1. Step 2, I'm looking at this set. 3, I'm looking at now the closure of this ball intersected with A. This here is compact. This here contains a subsequence. Of xn. This thing here is compact. This means that I can cover it by balls of radius, so cover it by balls of radius r/4. I want smaller radius as I'm going along, okay? So I'm covering it with, and in fact, I can cover it by finitely many balls. Right, why finitely many? This is because this here is compact. I'm writing this here as the union of balls of this radius, where anything in this set is a center, and so I have the finitely many of those cover it, right, by compactness, right? And so now what I observe is that if I take, and now I just had to be a little bit careful. So now I'm observing that if I take the ball of radius, the double ball, suppose I'm taking this ball here, so I get before that. So I have that it's now finitely many balls cover this, so this means that a subsequence must lie in one of these balls, right? So therefore, so this is the 5th step, a subsequence of the subsequence lies in one of these finitely many balls of radius r/4, right? And now now I take, so the next thing is I do, and now I want to apply the corollary from before, right? So I started with my space X. I got this ball here of radius r, and then there was some center. Then the next thing is that I get a ball of radius 1/4 r, and now this is with one of these other finitely many balls, where a subsequence, let's call it like this, maybe like 1 or something like that. Right, so I get that, so the balls of radius r/4, they cover this. So a subsequence actually would have to lie here. Right, and so now I want to use the corollary. If I need to use the corollary, I need to have nested, and I need to have closed sets, right? And so in order to make them nested, then I'm going to double this ball. Why do I double this ball? Well, I double this ball here because these guys here cover this, right? But it means, of course, that there could be something outside, right? There could be, so this is like a ball of radius r. And so then you have this ball of radius a quarter r. But the quarter balls, they may have some part outside and some part inside, right? So it's not, this ball here is not contained in that ball, right? But if you went to the double ball, if you went to this ball of radius 2r, right? You see this point here, the center, the center here, it would lie, right? There would be some points in this ball here that would be within. It may not be the center, but there's some point here that's within r of the center. And then by the triangle inequality, any other points is actually within r over 2 of that point. So everything is comfortably, so this thing here, and even the half ball, so I can conclude that even the ball of radius r over 2, even this one here, is contained in the double ball. Like that, okay? And in fact, if you make things less or equal to on both things, then you have that. Okay? Now what I have is, at least here, you have something that is nested, right? And you see that the radius went down, right? Right? So these are nested and they're closed, okay? And so now what we do is, so now we want to do this for a sequence, right? And then of course we want to, so now we want to construct a sequence of closed balls like this, right? And so, and now when you pick your subsequence, you have to, you can't wait with picking the first element in a subsequence, right? Remember, if you keep waiting, then you will end up getting nothing, right? So you pick at each stage, you pick one element in a subsequence, and then when you have the next ball, you pick the next element in a subsequence, and so on, right? And so, so we will do this with, so we're going to do this procedure here. So now we're getting back to the proof of the theorem, right? And again, remember the theorem was this, maybe I erased it now by mistake, but the theorem was this Bolzano-Weierstrass theorem for a metric space, that you have a metric space, you have a compact subset, and you have a sequence in this compact subset, and you want to construct a convergent subsequence. So, so what you do is, there's a proof of the Bolzano-Weierstrass for metric spaces. So, so what you do is, so you have this, again, A here is compact, and you have a sequence xn. This is a sequence that is contained in A. What you do is that first you can just let R be equal to 1. And then you do this, you cover it you have here A, and you cover it by finitely many balls of radius 1. And for one of these balls, you have that there's infinitely many elements in the sequence. So you're going to focus on that ball from here on and out, and you just pick in your subsequence, you now pick your first element in the subsequence to be some element in that ball. Then, so now the picture is that you just look at that ball, right? Forget about the other ball and everything else. You now cover it by balls of radius a quarter, right? And you have that, again, that's finitely many cover this ball intersected with A, finitely many cover it, right? And so one of them has infinitely many elements in this sort of subsequence that you consider. And so you just pick one element in that, right? That's the next one. And now you repeat this process, right? And so you see that for these balls, but remember that, so you're starting with a radius 1, but you have to double things, right? So the sequence of closed sets, the initial closed set, will have radius 2, right? And the next one won't have radius 1/4, but it will have radius 2 times 1/4, so half, right? And the next one will then be a ball. It will have a different center, and it will have radius 1/2. And then the next one, you see, at each stage, when I do it like this, then it goes down with a factor of 4 at each stage, right? So this here will be 1/8, and so on, right? And so you see that this sequence, these are these closed balls. They are nested as they should be, and the radii goes to 0, right? So this means that there is an element that lies in all of these, and that is now the limit. Because of the subsequence, if you are from here on and out, it would be like in that ball, and from later on and out, it would be in the next ball, right? So that intersection of all of these balls will be your limit, yeah. So, right, so really what you're looking at, that this thing here intersected with A, right? So it's just that these balls here, so the intersection here, that these are the closed sets, these are the compacts, each of them are non-empty, and they are the closed subsets of A, right? So you're really arguing on these guys here. You see what I mean? I know I stated it for balls in the call length, right? But if you just think about it, right? The balls play no particular role except for saying that the intersection of all of them contained just one point, and that was because the radii went to 0, right? The important points were that the sets were closed subsets, right? Because then there was the lemma was just all about closed subset. It had nothing to do with, and so you see that that these guys here are closed subsets of A, right? And so, yeah.
If I understand where the B substitute from, is it like you're looking at the ball of radius 1 and have to see how to contain the ball of radius 1/4?
So you mean why I went to double the ball? No.
Yeah.
Okay, so the reason I go to the double ball is that I want to make sure that things are nested, right? And if I just did this procedure, suppose, so again, I take this ball here. This is the first step. I have these balls of radius 1, and I find one of them so that there's infinitely many in the sequence. Then I want to have something finer, right? And so I chose, because I think you didn't quite have to do 1/4. You could actually have gotten away with 1/2, but I thought it wasn't as clear if I did it. So I did it with 1/4, because then I thought it looked more obvious. So if you now take this ball here, and as you say, you always have to intersect with A, right? But just to make things compact. But so I cover it with balls of radius 1/4, right? But some of these balls, part of it may lie outside this ball here, right? Because, I couldn't cover, you see, if I take a ball here, I can't cover it by finally many balls if I insist, just if it was like Euclidean space, if I insist that the balls had to be, this smaller ball had to be inside this ball, then there wouldn't be finite many. So I have to kind of look at balls where some of these balls is kind of outside the sets, right? But now, of course, so that wouldn't really work, because it's not like this ball here, let alone the double of this ball, is not contained in this. So that's why I doubled that ball. Then everything is comfortably contained in each other. Right? Any other questions? Yeah.
Isn't there, since they're all closed ball, or wait, no, these are open balls?
When I cover things they are open because I have to have, when I have a compact set, I have to cover it by open subsets. But then once I'm looking at the nested things, I have to go to the closure because otherwise the lemma in the corner would not apply. Okay?
And if they, hypothetically though, if they were closed though, you would be able to cover like B1 with a...
And I'm just saying that if the open balls cover it, then of course their closure also cover it because the closure is a larger set, right? But you know, it wouldn't be a priori clear that like it's not like they're closed sets, so that it's not working the definition. Yeah.
And then I'm not sure if we proved that like up there you have that like if you have a compact subset and take the intersection with a closed subset. But yeah, we proved that it's closed. Did we prove that it's compact?
We prove that it's compact, and I can prove it again because it's very easy. So, so if you have a metric space, this here is compact, and now you take a subset here of this here, and this here is closed. It's a closed subset of X. Then you look at X, take away B. You take any cover of this, together with this, they cover A. But then finally many, but this here have nothing in B. So actually, finally many of the other one cover B. Yeah. Any other questions? Okay, great, thanks.